Thank you. Okay, 12, what was 12?
1 over the square root of x squared plus e to the negative 3x.
Is it 5x or 3?
3x.
Okay, so that's f. So f prime, well, first thing I would do, well, you guys tell me, first thing we should do is what? We should write that as 1/2 power, and since it's on the bottom, make it negative 1/2 power. So I would rewrite this as that, right? I would not do, remember this is the one I talked about not doing a quotient rule on. You do not want to do a quotient rule here, because chances are you'll mess it up. You could do a quotient rule. Chances are you'll mess it up. So I would rewrite it like that, okay? Now, this is just a power rule, right? This is u raised to the n, which is n times u to the n minus 1 times the u prime, right? It's just some stuff raised to a power. So we bring the power down, we leave the inside alone, we drop the power by 1, which would be that, and we times by the derivative of the inside. Okay? So what's the derivative of the inside? Well, it's 2x, right? Here's our inside right here. So 2x. Now, what am I going to have to do when I do this derivative? I'm going to kick out a negative 3. Now that's its inside, right? So we could just say the derivative of e to the u, e to the negative 3x is e to the negative 3x times the derivative inside, which is negative 3. But we've done that once so much, we just know we're going to kick out negative 3. So just to save myself a little time when I do it, I'm just going to go ahead and do it right away and put it out there, right? But you could have had 2x plus e to the negative 3x times negative 3, but then you're just going to rearrange that anyway. I think you should, like that, okay? So that's it. Now, do you need to take that 1/2 and distribute it? You can't distribute it here, right? You can't distribute it through something's got a power on it. But you could distribute it through that, but I don't think that gains you. Now, to be honest, if that was a 4, then taking the 1/2 through there maybe is okay. But usually distributive, I don't really care if you distribute through. It doesn't matter to me, right? If you get one, just do a simple one. If you get one that's this, or you write it as 2x minus 6, I don't care. The only reason I would ever want something factored, in case I could cancel. Sometimes on quotient rule, that happens, where you can cancel something. So sometimes you want to be on the lookout for that. But otherwise, I don't care. The 2 answers like that, either way. Okay? We're going to practice some more of these here in a little bit. So, okay, can we go to 21? You got another one? 15. What about 15? What's 15?
So it was 1 with a cosine squared.
Okay, so read it to me.
F of x was cosine squared of x to the third.
This?
Yeah,
Okay.
so then you can rewrite that as like cosine x to the third squared.
I think you have to. Rewrite it like that, right? I mean, I'm not very good at it.
Yeah.
I've got to rewrite it. So, start on the outside, right? So this is a u to the n problem.
Yeah.
So you bring down the 2, cosine of x cubed. To the first, I probably won't write it, but just so you understand, right? That's what we'd be doing. I mean, if this would have been cosine to the 5th here, right? If this would have been cosine to the 5th, this would be important. We bring down a 5, and then this would be a 4, right? But since it's a 1, it doesn't really matter. And then times the derivative of the inside. Well, what's the inside? The inside is this, right?
Negative sign.
So now we're doing a cosine u problem. Now we're doing a cosine problem. So what's the derivative of cosine? Negative sign, leave the inside alone, times the derivative of its inside. But that's all got to stay in here, right? That's got to stay in these parentheses that I'm doing the derivative of the inside here. But its inside is x cubed. So what do you get? 3x squared. Now, as you step back and look at it, usually when you get into a problem like this, you got to step back and look at it and say, what do I got? Well, really, all I have is 1, 2, 3, like 4 things multiplied, right? So I got an A times a B times a C times a D. Now, I can just rearrange those however I want. So I would take this 2 and this negative and this 3, and I would put those all out in front. And then the x squared I would put out in front. And then cosine x cubed. Now, where you got to be careful, see, this is how I think that should be written. Okay? But you gotta be careful, because if you get plus signs in there, then all of a sudden that changes, then all of a sudden you can't just start stripping things out, right? This has been a 3x squared plus 1 in parentheses here. Now all of a sudden that, that's different. You gotta treat that as a thing, right? But we just got 1, 2, 3, 4 things. Put them all together, rearrange them like that. Okay? All right, now can we go to 21? So 21 now, to be honest, gateway test, and I know that's foremost in your mind is the next quiz, and you want to focus on that, and I get it. These problems we were doing here, this is what your gateway test is like, right? Not these problems, right? But they're still important because they're going to show up on our midterm, they'll show up on the final, these kinds of things with tables and graphs and stuff, we still definitely want to do. So on 21, oh, this one had the table, didn't it? Okay, so I just went through here. So on 21, we're not going to fill in the whole table, but we'll just do an example like 1. Okay, the first column. So X is 1. So they want H of 1, right? So that first blank entry there, they want H of 1. Well, what that means is you put a 1 everywhere you see an X, right? Everywhere there's an X, you put a 1. So we're going to have F of G of 1. Well, what's G of 1? 4. So this now becomes F of 4, right? Well, what's F of 4? 3. So there's your answer to that one. Okay, but now the entry below that, they want H prime of 1. Well, here's H prime of X, right, by our chain rule. So that means H prime of 1, we put a 1 in for X. So we got F prime of G of 1 times G prime of 1. So what's G of 1? 4. So this becomes F prime of 4 times G prime of 1. Well, what's F prime of 4? 4. And what's G prime of 1? 3. 4 times 3 is 12. And so that's how we get H prime of 1. And then you repeat that for 2 and for 3. Okay? All right. 22. Okay? They say that H is equal to this, which is quite the mess. They give you all this other stuff, and they say, what's H prime of 1? Well, as I've said to you many times, before you can find H prime of 1, you need H prime of X. So you have a place to plug the 1. So H prime of X would be the derivative of this. Well, we'd start by doing the derivative of the outside, leave the inside alone, times the derivative of the inside. So it would look like this. Derivative of the outside, F prime, leave the inside alone, times the derivative of the inside. Derivative of the inside would be the quotient rule. The quotient rule says do the derivative of the top, G prime, leave the bottom alone. Minus the top left alone, derivative of the bottom, 2x. All over the bottom square. Right? So that's just your U prime V minus UV prime all over V squared. Quotient. Now we have to just plug a 1 everywhere. Now we just got to stick a 1 everywhere. We got to stick a 1 there, and there, and there, and there, and there, and there, and there. Okay? So we do that. So now what's G of 1? Well, they told us. G of 1 was 2. 2 over 2 is 1. So this becomes F prime of 1. G prime of 1, they told us, was 4. G of 1, they told us was 2. So we have 4 times 2 is 8. 8 take away 4 over 4. We get 4 over 4, which is 1. And so F prime of 1, they told us was 7. So 7 times 1 is 7. That's it. Okay? 26. And I don't know, I might be skipping some, but these are the ones I want to look at. Okay, now there's a graph. Now you have to look at the graph in your book on page 176. It basically comes down and goes like this, and it hits, it's got a low point here at, look, it crosses right with the origin, and right here at 2. It's got a low point. Okay, so that's the F graph right there. Okay, so they they tell you g of x is this, so g prime is this. Everybody go with that? You got derivative of the outside is f prime, leave the x squared alone, times derivative inside is 2x. And so in 26, they said, where is g prime equal to 0? Now, we're going to need this on 31 that we're going to do here in a minute, which gets a little tricky. Where is g prime 0? Where does this equal 0? Well, either where one of those two is 0. Okay? So, where is f prime of x squared equals 0? And then where is 2x equals 0? That one's easy when x is 0, right? So we got that, right? Now remember, that's the f graph over there, but we're asking about g, right? See, that's where you got to make sure you're not confused. Now on this one, what's this mean? Well, this is where everybody gets messed up on this. And several people came in this morning and were asking about it. Forget the red part for a minute. They're just asking, when is f prime, because we've done this before, right? I've asked you that question where I didn't even have anything in the parentheses. Where is f prime 0? Well, what would you say? At 2. Now, when you tell me that, what you're normally saying is that this is 0 when x is 2, right? When the input is 2. Well, now on this one, so f prime, so we can tell by looking at the picture that f prime of 2 is 0. Well, that means that the red thing has to be a 2. Well, usually that's just an x in there, and we want to know what x is. Well, this time it's x squared. So what does x have to be? Yeah, if x squared, if this thing has to be a 2, then x squared has to be a 2, which means x has to be plus or minus root 2. So it could be plus or minus, even though there's not really being negatives over here, but it could be. So those would be our stationary points at g. That's where g would have stationary points. That's where g prime is 0, at 0 and at plus or minus 2. Okay? And that's how we would get that. Okay, it's just notation, function notation. Okay, let's go on to 31. Okay, 31 then is very simple. It said let h be f of g of x. They use the fog notation, but there it is. And then it says what values of x correspond to stationary points of h. Well, that means stationary points is where is h prime 0. So where is this 0? Well, we need to answer these two questions right here. So the easy one is where is g prime of x 0, right? One of these has to be 0. And then the harder one is the second one, as we just saw. So this is very closely related to number 26. So once you do 26, this one you can kind of do, but it's still a little harder. So we got our graphs over here. So now, where is g prime 0? We go to the g graph, looks like right there. Now that's a weird one. That's kind of a funky little thing there. But I think if you look at the answer book, they said 2.5. And right there, right? So that's at negative 1.5 and 2.5. Everybody okay with that? Right? That's easy. So that's where g prime is 0, and if g prime is 0, that's going to make h prime 0. Okay, now what about this one? F prime of g of x. Where's f prime? Well, again, let's ignore, I'll put it in blue this time. Let's ignore the blue part. Okay, so where is f prime 0? At 0, 2, does it look like it's 0 down there? I mean, we're just talking about the slope now, right? Where is f prime 0? F prime, the slope seems to be 0 there, and it looks like it's flattening out there. It looks like it's flat. Now, we don't know, it might be a flat spot, might go back up as a local max. I don't know. Doesn't matter. It looks like the slope is 0 at those places. So it looks to me like f prime of 0 is 0. It looks to me like f prime of 2 is 0. Would you agree with these statements? And it looks to me like f prime of 5 is 0. Right? Would you agree? Okay. Well, so what does that mean? That means in the parentheses here, we need to get 0, 2, or 5. But what's in the parentheses? So we need g of x to equal 0, or we need g of x to equal 2, or we need g of x to equal 5. In other words, the way a composite function works is the outputs of this one are the inputs of this one, right? So we need the outputs of this to be the inputs for my f prime. Well, my inputs for f prime need to be 0, 2, and 5. So we need the outputs of g to be 0, 2, or 5. Well, where does g have outputs of 0? Right there, which is at negative 4. Right there, which is at 1. And right there, which is at 5. So let's think about that a minute. So if x is a -4, what we're saying, let's go all the way back up to here. It's kind of like we did the table. So if x is a -4, we put a -4 right there. We're going to have g of -4. What's g of -4? G of -4 is 0. Okay, so this will be f prime of 0. What's f prime of 0? Oh, f prime at 0 is 0. So sure enough, that would make this be 0. Does that make sense? Okay, and what about 1? Put a 1 there. G of 1 is 0. F prime of 0 is 0. What if x is a 5? We would have g of 5. G of 5 is 0. F prime of 0 is 0, right? See what I'm saying? So when does g a 2? Right? Here's 2 right here, right? When does g of x have outputs of 2? Well, right there at -3. And what about right here? At 0. Oops. So it looks like if x is one of those, we'll get it, right? Let's try it. Let's put -3 in here. G of -3 is 2. F prime of 2, oh, the slope at 2, 0, right? So we're working it backwards. When is g of 5? Never. So what are our answers? Right here, so these 2, these 3, and these 2 here. So those 7 places are stationary points of age.
What would the graph of
Oh gosh. I don't know. I have no idea. I mean, we could figure it out. We could just start plotting points. You could put a 1 in. And what's g of 1? And then what's f of that? And then you plot that points. You can start plotting some points. But you know where the stationary points be. So you know where they, you know. But yeah, they could be flat. Who knows what. All right. So, website. So I'm going to show you, you don't need to pull this up on yours, but on our website, if you go down to web links, derivative practice 1, derivative practice 2, and derivative and antiderivative practice 3. Now, you don't have to do the antiderivative ones, obviously, just the derivative ones. Okay? So let's take a look at this. And also, turn in your book to page 195. I mean, there is so much practice here for you that there's no excuse, I mean, really, to not have all the practice you want and then plus come in the morning and talk to me and get help or whatever between now and Tuesday. Now, we do have a couple one more rule we're going to talk about tomorrow. We got kind of this odd little other way of doing derivatives for some special situations that we got to talk about today. But the vast majority of the problems on the gateway test, and you could probably get 8 out of 10 just by knowing what you know right now. Even without the 2 new things we're going to do, it's close. You get 7 out of 10 for sure, just by knowing what we know right now. Okay? So if you look at page 195, look at all those functions, and then go over to page 196. Okay? So you got all kinds that you can practice there. Now, those are ones that are pretty much just on the stuff we know so far. I don't think there's any of the inverse trig in there. Oh, maybe some at the end of 196, but those are even anti-derivatives, so we won't get into those. Okay, so page 195 has tons of practice. I've also got some websites here that you can go to. So why don't you just in your notes here, we're gonna throw out a few problems. What time is it? 8:40. Okay, so we got a little bit of time here to just. I'm going to just throw up some and let you practice and just let you see what these websites are like. Okay, the first one. Derivative practice number 1 takes you to this website here. Okay? Now, this is interesting. You can pick your level. 1, 2, 3, 4, and quite nasty. I wouldn't worry too much about quite nasty. 2 is a pretty good level of practice. You can also pick which functions you want to deal with. So like right now, if we want to just stick to basic e to the x, sine, cosine, natural log, that'd be good. If you're afraid that you might run into a 2 to the x or a log, one of those, maybe that'd be good. And then you're like, yeah, let's practice some tangent too. You can click those, right? Now, these ones with h's at the end, we're not going to learn about those, so you have to worry about this. Matter of fact, this whole bottom row you have to worry about. The inverse trig, arc sine, arc cosine, when we get to those, you can click on those. Matter of fact, if that's all you want to practice, right? If you say, you know what, I want to practice some of these new inverse trig ones, you can just do this. And then you can just hit start over. Now it's going to give you some regular algebra ones. It says polynomials, rational functions, power functions. So it's going to give you some typical power ones. But then it gives you that right there. Okay, but let's say we don't want that. So we want to just do, how about some of those? Yeah, let's throw in the logs. Okay, so right there. Okay, everybody do that. 5 sine x e to the x right there. Okay, I'm going to put up my answer. Don't look if you want to see it again. All right, you agree with that? Now, little comment here. If I have the function 5 sine x e to the x, I'm treating that, I'm just connecting that 5 with the sine. Did you do that? Instead of saying, because we have said, well, the 5 just hangs out there. Well, you could have said, well, the 5 will just hang out there, and then I have to do a product rule. But then you got to distribute and all that, right? So if I've got 5 sine x e to the x, I'm like, okay, that's a product rule. I'm going to attach that 5 to the sine. So I can do that anytime it's just a constant. And treat it as part of it. Then I don't have to worry about the distributing. It just goes with it. Especially when you have negatives, that's important. Like if you had a negative e to the x sine x or something like that. Okay, now, the nice thing about this website is you can type it in. So what did we say? 5 sine x e to the x. And they kind of tell you how to enter it. Was that right? Well, it was actually cosine first, wasn't it? But it doesn't matter since it's plus. I probably have to do a time sign, I'll bet, back here. I probably have to do a time sign right there. Okay, and then we submit our answer, and it says correct. So that's nice, and even though we had it backwards maybe from what it could have been, we get it. All right, let's do another. I guess you just do start over.
It already gave you one after you.
Oh, it did? Oh, I don't like that one. These are too easy. Okay, let's bump up to 3. Really? That's a 3? Oh my God, that's too easy.
Let's go quite fast.
Let's go. Hang on a second. Oh my God, that's a triple product rule. I doubt you're going to do many triple product rules. Let's do it. Oh, that's awful. That's awful too. Try that one.
Do we have?
Yeah. Try that one. Square root of that stuff right there.
out a sheet that you can attach.
Oh, yeah, I could do that. I will. That rule sheet, you mean?
Yeah.
Yeah. Yeah, you know, I'm trying to save paper, do things electronically. Maybe you guys should print it off, but whatever.
We can't print off of our program.
I, in a perfect world, we could just do that, but I'll print. All right, I'm gonna put up what I got. Now notice, as messy as this one is, there really isn't any simplifying or anything to do afterwards. I mean, we're going to talk over the course of the next several days before next Tuesday. You'll be pulling your hair out sometimes on simplifying things. Quotient rule, sometimes that's a more common place to have to simplify because the top can usually simplify, and then sometimes you can cancel. So that's a place for some simplifying. But a lot of times, there's not that much to do. I mean, there really is not much I can do here. Now, the first thing to understand is it was this mess to the 1/2 power. So you start off by doing the power rule. So you bring the 1/2 down, you leave the inside alone, then you drop the power by 1, which makes it -1/2 times the derivative inside. Now, if you'd have watched me do this, I did a times sign, I did this parenthesis, and I went way over here and wrote this parenthesis. I knew I was going to have a big mess in the inside because I could tell I had what right here? I got a product rule right here. So I knew I was going to have a u prime v plus a uv prime. I knew I was going to have that. And then I got this plus sign, so I knew I was just going to do this on its own. Remember, the way you do plus minus, you just do the derivative of this plus the derivative of this. Well, when I do the derivative of this, I'm going to have to do a product rule. So I know that's going to be a kind of a mess, but then plus and then whatever this is. And that's all got to be in those parentheses. So the derivative of the cosine's negative sign times that left alone plus the cosine left alone. Derivative of e to the x is e to the x. And then the derivative of the log is 1 over x, or 1 over the inside, which is just x. So 1 over x, 1 over ln2. And, I could stick those together as one fraction, but, that's not a big deal. And that's pretty much all you can do there. Because now it's this thing plus this thing plus this thing. And they really can't go together.
Oh, we're gonna have to do like triple product rules.
I don't think so. There was one there. The thing with the triple product rule just means, if you have A times B times C, you just treat that as one thing. And then you treat that as another thing. So this is your U, this is your V. So it's U prime V plus UV prime, right? Well, when you go to do this, the U prime, you're going to have a product rule, right? So then you're going to have to do a product rule when you do the U prime. So you'll have da-da-da plus da-da-da, just for the U prime. And then you'll have the V, which would be the C, right? So this would be like A prime B plus AB prime, right? So you would do that. And then times the C, and then plus the U left alone, which is just the AB, times the B prime, so then you'd have the C prime. You know what I mean? So you would just treat that as one thing times another thing, and then do it that way. So that would be a triple product rule. But I can't think over the course of this year how many times we'll even have that. So I don't know if it's a big deal. Okay? All right. So I'm not even going to bother with typing that in. It's nice sometimes to type it in to see if you're right. And there's so many ways you can screw that up typing it in that who knows. Okay? So that's one website. Okay, let's go back here. Let's go to derivative practice number 2. This is from Arizona State. This is quite old. So I always have to check each year to see if my websites are still working, because a lot of times they're not. If we go back to this one, I don't know. This is from Bluffton University. You can tell that these are they just call this derivative test. But practice 1, and it's got solutions. Now this just comes up as a PDF. Okay, so these are a little easier. Practice 2, they get a little trickier. Okay, but the nice thing is they have answers. And then practice 3, a little bit trickier, yeah. And those get into some arc tangents Here's the new thing we're going to do here in a little bit. See how this has 2y equals x squared plus sine y? It mixes x's and y's all over the place. Those are relations. They're not functions, but they're relations. We have to be able to deal with them. So here's another one, right? So we're going to have to do some of those too. Here's another one with x's and y's kind of mixed in. Here's another one. Okay, so we're going to get into that. So you get some of those in there. So let's go to practice 2, and let's just pull up one here. Let's do. Well, let's do number 8 here. Nope, that's 1 minus sine squared.
I'm going to reveal my answer.
Okay, so if that was number 1 on the gateway test, how many people would be 1 for 1?
Wait, that's your answer?
That's the answer.
Well, I have options.
No other answer would be sufficient there. Unless I messed it up. You get it?
I didn't
Yeah, did you cancel a bunch of stuff?
I did. Not a bunch of stuff.
You can simplify it and turn cosine squared into 1 minus
No, I don't think. Well, yeah, you can. I was. Well, I'll show you. I'll show you what. All right. So let's run through it because it starts out to be a big mess,
Oh, I got
right?
that part.
For sure. So let's run through this. So starts out with a power rule. So we bring the 2 down. We leave the inside alone to the first power. A lot of times you can't do Oh, I'm sorry. I did, see, I'm over one. I missed it too.
Yeah, that's right.
But no, what I showed you is what I had for this.
Oh, you still have
You still got this stuff over here. I forgot about that. Talking about the forest for the trees, right? You get so caught up, I got so caught up in this that I forgot that I had this over here. So, but let's go ahead, let's keep talking about it. I just realized that as I wrote that. So you get this, and now we gotta do the derivative of the inside, which is gonna be a big quotient rule. Now what I did, again, is I put a big set of parentheses, and I drew a great big long fraction bar, all right, and then I started working on this. So, what do you got? Quotient rule says derivative of the top should be negative sign, times the bottom left alone, don't forget parentheses, minus the top left alone, which is cosine, times the derivative of the bottom. Now, derivative of 1 is 0, and derivative of sine is cosine, so you have a negative cosine. That's where this negative cosine came from. And then all over the bottom square, which is this. Now, again, well, this would not be just cosine, right? This is not the same as 1 minus sine squared, right? This is 1 minus sine times 1 minus sine, which would be a whole FOIL thing. So this is not just cosine, right? You can't just distribute that square and make that 1 minus sine squared, okay? So that doesn't simplify there. But what you do want to simplify in a quotient rule usually is the top, right? So negative sine times 1, negative sine times negative sine. And then here you take your negative cosine times your negative cosine. So what happens on top is you end up with negative sine times 1. Negative sine times negative sine is positive sine squared. And negative cosine times negative cosine ends up being a plus cosine squared. Now, what's sine squared plus cosine squared? That's just 1, right? That's what I was hoping would happen. I saw that if I distribute, I saw I was going to get some sine squared, cosine squared, so I was hoping. Now, sometimes you hope, and it ends up being sine squared minus cosine squared. Well, that doesn't work then, right? But if it's sine squared plus cosine squared, that's just 1. And so I get 1 minus sine, and then the bottom is 1 minus sine times 1 minus sine. So one of these here cancels with one of these here. And so I end up with 1 over 1 minus sine. But then I got to remember this stuff. So I end up with 2 times cosine x over 1 minus sine, and then times 1 over 1 minus sine. Now I could leave it like that, but it's basically 2 cosine on top and 1 minus sine quantity squared, because you just times your top bottom. That would be the best answer. So see, I screwed up already. I got all. Yeah, you had it. So you had those there, yeah. So that's good. That's good. Okay, there's a lot of stuff there. Now if we were talking about the gateway test and we were breaking it apart into 10 problems, I would say I'd try to shoot for maybe 3 that I would put in kind of the easy category, and maybe another 4 or so that are in the medium category, and then maybe 3 on the harder end of things. This would be a hard one, okay, because of the simplifying and stuff you have to do, right? That one, but the one we did here a minute ago with the product rule inside there, to me, that's a pretty easy one. Maybe medium. I mean, I wouldn't spend a lot of time worrying about is this an easy or medium, whatever. But there wasn't really much simplifying to do. You just had to know your rules and go through them. This one just there's a lot of places to get lost with pluses and minuses and stuff like that. But there it is. There's your derivative. Okay, there's your derivative. All right. So the third website is the third link is a new one that I just found. Or it's an old one, and then the link didn't work, and so I kind of searched and I just found that new link. The Math 140, they call them gateway exams too, and this is, where is this? Jacksonville University. Okay, and so they've got a bunch of different ones, and I haven't really through them, but then they got the solution. So 140 is their derivatives, and then 141 are anti-derivatives. So you can go through here, and so again, it's a PDF. Now they do what they do is they do 8, and then you have to get 7 right. Now, it doesn't look like most of theirs have any of this new thing we're going to learn. Theirs look a little easier, but you got to get 7 out of 8. So it's got some product rule and some some stuff like that, and so forth. So there's a lot of different places. Basically, bottom line is a lot of different opportunities to practice. To be honest, you could get a lot of practice just doing page 195 of the book. To be honest with you, so don't forget about that. All right, let's move on then with this other thing we want to talk about today. So what we've got, this is called implicit differentiation. Implicit differentiation. Now, implicit, the word implicit comes from imply. So to imply something means to not say it directly, right? So you have to imply, well, that's just it. It means it's not directly stated. Okay? So normally when we deal with a function, they are explicitly defined. They are right there in front of you. They are plainly stated. That's an explicitly defined function. That's what we're used to seeing. X is the input, which sometimes called the independent variable. Like think about when you're doing a table, you can plug in anything you want for X, right? That's independent. It doesn't matter. You just put in anything you want. And then the Y, the output's the dependent variable because it depends on what you put in for X. The output depends on what the input is. So we call that the dependent variable. But the only reason I say that is in an explicitly defined function, it's very obvious. You got the output function over here by itself. You got the input function on the other side. It's Y equals. In an implicitly defined function, and it might not be a function, because like sideways parabolas, I didn't put that one up here. Well, actually, I kind of do. Well, no, that's not a sideways parabola. If you have like x equals y squared, y is still the output, and x is the input. But it just doesn't seem that way the way it's written. That's a sideways parabola. It's not a function. So a lot of times these things, ellipses, hyperbolas, right? You remember circles, right? X squared plus y squared equals 16. That's an implicitly defined relation. A relation is just a set of ordered pairs, so it's not a function. So these are graphs also. And it makes sense that a sideways parabola has slopes. A circle has slopes on it, right? So we need to be able to find the y prime on those as well. Okay, so this thing called implicit differentiation is just saying doing the derivative on relations or equations that are implicitly defined. All right, so what we're going to do these is we're going to say do the derivative of both sides. Now, in the past, we've never had to say that. If I give you y equals x squared minus 2x, we've just said take the derivative. Well, think about it. Do the derivative of both sides. Well, what's the derivative of this side? Well, 2x minus 2. What's the derivative of this side? Yeah, what's the derivative of y? Y prime. But then, when you start thinking of it like that, you start thinking, wait a minute. The derivative of x is just 1. How come the derivative of x isn't x prime? Right? I mean, how come the derivative of y is y prime, but the derivative of x is 1? Well, here's why. Because it's what you're doing the derivative with respect to. We haven't made a big deal about that, but on your calculators you have to. Remember when we use this notation here? When you do the derivative of y, the output variable, with respect to x, we call that y prime. But if I tell you to do the derivative of x with respect to x, what would Leibniz call that? No, he wouldn't call it x prime. He'd call it dx over dx. The derivative of x with respect to x. Well, what does that look like? That looks like 1, doesn't it? dx over dx looks like 1. So it fits with what we've been saying. The derivative of x is 1. Why? Because we're doing the derivative with respect to x. So the derivative of x with respect to x is 1. It'd be like dx over dx. The derivative of y with respect to x is not just 1. It's y prime. Make sense? The difference is doing the derivative of the input variable as opposed to the derivative of the output variable. We do the derivative of a y, it's y prime. Okay, make sense? I think this notation is an important way to think about it. When you're doing the derivative of y, you're doing it with respect to x, the derivative of the output variable. So we're doing the derivative of y, we call that y prime. Now that hasn't been confusing up until potentially now, because that's just what we've always done. Y was, we always had equations like this. But now we got to think about what happens if we have equations like this. Derivative of x squared, yeah, 2x. The derivative of the x, 1. Okay, easy. But what's the derivative of 3y? What's your guess? The derivative of 3y is going to be 3y prime. Right? It's going to be 3, because the 3 is just going to hang out there. And then what's the derivative of y? Y prime. What's the derivative of 2x? 4x, right? What about that? I don't even know. What about the derivative of y squared? Just a guess. We're going to talk about it here in a minute. What do you think the derivative of y squared is? You think it's 2y prime? Not quite. You're close. No. We have to do a power rule. He's right. You got to bring the 2 down. No. No. It's the same power rule. You still drop the power by 1. It's 2y, y prime. I'm going to show you why right now. All right. So, first of all, what's the derivative of y equals x? If I just asked you, before we started this discussion right now, tell me what you would write down right here. You'd write y prime equals 1, right? What would you do on this one? If I said y equals t, what would you write down? You'd write down y prime equals 1. What if I said y equals z? What would you write down? Right? Because in each of those cases, you assumed y was the output variable and the other one was the input variable, right? Now, I claim on this one you were doing dy over dx, right? You were doing the derivative of y with respect to x. On this one, you were doing dy dt. You were doing the derivative with respect to t. And on this one, you were doing dy dz. You were doing the derivative with respect to z, right? That's what it means. So on this one, like we were just saying on the other page, yes, well.
If you don't reference that dy is respect to dt, you just assume that y is
yes. I think we assume that y is our output variable. If there's a y in there, we're assuming y is our output variable. And on the quiz, I'm just going to give you all y's and x's, so it's going to be obvious. Yes, well, on these, you're not, what you're assuming is the thing in the brackets is on top. So you're saying the derivative of that with respect to x, right? So that's why on that derivative rule sheet, everything's with respect to x. So even when we have a u there, the u is like an output variable. It's a bunch of x's. It's a function of x, and that's why we tack on a u prime. It's a du over dx. It's a derivative of u, whatever the inside is, with respect to x. So on this one, like I was telling you, 3y, the derivative is just going to be 3. You do the derivative the same way when there's a y. The difference is we have to tack on a y prime, and I'm going to show you why we have to tack on a y prime. So the derivative of 3 is going to be 3 and then y prime. And on this side, it's just going to be 2x minus 1. Right? Now, we would want to finish that by dividing by 3, because we want our final answer to be y prime. Right? So we would finish that. Now, here's where it gets tricky. So I was just telling you about this one. So so on this side, it's easy. This is 12x squared plus 2, right? But on this side, it's going to be, pretend that this was just normal like an x. What would you say the derivative of y squared is? You'd say 2y. But we're going to also tack on a y prime. Now, why are we tacking on a y prime? Well, I'm going to show you here in a second, but the derivative rule sheet kind of shows it too. Do you notice on every one of those derivative rules that we do on there, at the end, or those ones at the bottom left for sure, at the end we tack on a what? A u prime. Why do we tack on a u prime? Because that's the derivative of the inside. We assume that the inside is some stuff. So we tack on u prime. Well, that's kind of the same thing here. So let me show you this. So this is what I've got. So let's pretend instead of y, let's pretend it was f of x. So this is a little bit like your homework's been the last couple. You don't need to write this part. It's up to you. You sure can. It's up to you. In case you ever come back and look at it. But I'm just trying to show you this to get you to understand. So 3y, let's pretend that just said 3f of x, and I told you to do the derivative of it. Well, what would you do? You'd let the 3 just hang out there, and then what's the derivative of f of x? F prime of x, right? That makes sense, doesn't it? So it'd be the same thing here, because y is the output, so y is like the f of x. So 3y should be 3 and then y prime, right? That one kind of makes sense. But now this is the one that always gets us, right? In the beginning anyway. But what if I wrote it like this, and I told you to do this? This is kind of like yesterday's homework a little bit with the chain rule and all that. What would you do for this derivative? Doesn't this have some inside stuff? So you'd bring the 2 down, you'd leave the f of x alone, and you'd multiply by the derivative of the inside, wouldn't you? So it's the same thing here. So it's almost like we have to, but this doesn't feel as much like an inside, right? It doesn't, but it is. The y is a function of x. A y is a function, right? So this is some stuff squared. So we're going to bring down the 2, leave the y alone to the first, times the derivative of the inside, y prime. Now we never do that with x, because we're doing it with respect to x. So you're never going to tack on an x prime, at least right now. Now later, remember when we had a particle moving on the x-axis and we had a function that was x of t? Well, when you do the derivative of that, you get x prime, because that would be dx over dt, right? So we'll never use y as the input variable, but sometimes we have x as the output variable, right? So there is such a thing as an x prime when you're doing something like that, but we're not doing that. That'd be like the lion moving and stuff like that. Okay, so we're not going to get into that here. So we could have an x prime, but in these problems we're not going to have an x prime, because what is x prime? In these problems, x prime is 1. It's dx over dx. So you could, I guess if you had 2x, you could go, or if you had x squared, you could go 2x, tack on an x prime. The problem is x prime is just 1, right? X prime is just 1, so why do it? But in these, we don't know that, so we have to tack on a y prime. So y squared is going to be 2y, y prime. Now, at the end of the day, here's what I'm going to end up telling you. In these problems, when you have a mix of x's and y's, whenever you do the derivative with a y, do the normal derivative, stick on a y prime. That's all you got to do. Do the normal derivative, stick on a y prime. So, what's the derivative of y squared? 2y. Stick on a y prime. So it's going to be 2y, y prime. Do the normal derivative, stick on a y prime. So, sine of y. What's the derivative of sine of y? Cosine of y times y prime. What's e to the y derivative? E to the y times y prime. In other words, we're just saying, hey, this is some inside stuff. So we got to do the derivative of sine is cosine, leave the inside alone, and then times the derivative of the inside. The derivative of y is y prime, right? Derivative of y is y prime. If it was x, we wouldn't worry about it, because x prime is just 1, right? Because it's with respect to x. All right, so at the end of the day, that's what you do. So let's say we had this problem here, and we wanted to know, I don't know why I put, so I got this equation, which is just a sideways parabola is what it is. Okay, so let's do the derivative of this. We want to find y prime. So what we want is y prime equals, right? So what we're going to do, we're going to do the derivative of both sides. All right, so here we go. So this is what some of your homework problems are for today. So when you see a mixture of x's and y's like this, now one option would be to solve it for y, but there's going to be some problems you can't do that. Like we could solve this for y, right? We could get x equals y squared, and then we could square root both sides. We have plus or minus square root of x, which is x to the 1/2. Then we could do our y prime like normal. We get plus or minus 1/2 x to the negative 1/2. Right? We can do that. But some problems you can't get the y by itself. You can't solve for y. So let's go through it. So what's the derivative of the left side? Okay, derivative of x is 1 minus 2y y prime equals the derivative of 0, still 0. Now we just got to solve for y prime. So I would just add the 2y y prime over, and then I would divide by 2y. Understand that in your answer, you're going to end up with both x's and y's a lot of the time, or in this case, just y's. That's okay. In an implicit differentiation problem, you may end up with just y's. Now, it turns out that's the same thing we got over here. If you don't believe me, let me rewrite the one I got over here. I got plus or minus, this would go to the bottom, so I got plus or minus 1 over 2 square root of x. Now, what was y? Y was plus or minus square root of x, right? So, there's my plus or minus. Here's my y down here. My y was square root of x, so it's 1 over 2, right? I mean, it's the same thing. Okay? Now, if I wanted to do some slopes, like what's the slope right here at the 0.4, I think that's the 0.42. If I put a 4 in for x and a 2 in for y, 4 minus 4 is 0. So here's the 0.42. So what's the slope right here? Well, we plug what in? What would I plug right here? I plug a 2 in, right? Because it's a y. So at that point right there, my y is 2. So I plug a 2 in there, I get 1/4. The slope would be 1/4. Well, that's about right. Right? Down here at negative 2, right? Here would be negative 2. Put in negative 2 for y, you get negative 1/4. Seems about right. Right? We're used to plugging the x in. Well, if we were going to plug the x in, let's take the one I did over here. We'd plug the x in, which is 4. What happens if you put a 4 in here? You get plus or minus 1/4. Well, if x is 4, that's why this isn't a function. If x is 4, it's got 2 different places, right? So we get 2 different slopes. So when x is a 4, we get a plus or minus 1/4 as our slope. Make sense? So we could have solved for y and done our derivative normal, or we can just do that. Now, sometimes we get problems where we can't. Well, we can solve this for y. Let's go ahead. Yeah, we got time. We got time. Real quick, let's do this one. This is just a circle. It's just a circle radius 1. Okay? So, what's the derivative of x squared? 2x. Plus, what's the derivative of y squared? 2y y prime. Whenever you do the derivative of a y, you do the normal derivative and you tack on a y prime. Equals? No. What's the derivative of 1? 0. Remember, you're doing the derivative of both sides. So you're doing the derivative of the left, you do the derivative of the right. Okay? All right. Now, we want to do what next? Solve for y prime. So we'll subtract the 2x over. We'll divide by 2y. 2's cancel. And there's our y prime right there. Okay, so right here at the point 1, 0, what's the slope? Well, you put a 1 in for x and a 0 in for y. What's 1 divided by 0? Undefined. Oh, look at that. What would be the slope right there? Be vertical, right? Be vertical. Okay, so it would work, right? And so forth. But you would, if you wanted to get slopes, you'd have to plug them into both the x and the y. But it's normal in these to have both x and y in your answer. Okay, let's do this one. Yeah, it's the last one. Last one. Okay?
So are we like showing how to find the slopes of conics?
No, I mean, the only reason I put the conics on there is those are good examples of equations that have both an x and a y in them, and you can't solve for y, right? But clearly we understand that an ellipse would have slopes on it. This is actually a tilted ellipse here. This would be a slanted ellipse is what this would be, okay? Matter of fact, I could probably go on Desmos and just type that in. I think it would graph. But so clearly there'd be some slopes, but we can't do this explicitly. We can't solve for y. Now hang on a second here, because there's something kind of tricky going to happen to you. So let's start. Derivative of both sides. What's the derivative of 5x squared? 10x. Now, what about this guy right here? No. 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 Product rule. Because we got two. I love that thing. So it's a physics. We've got two functions times each other. We've got negative. Now, here's where, and I talked about this before. The negative and the 6, I would connect. I would just keep those together. Otherwise, you're going to have to distribute that negative. So keep the negative with the 6. Negative 6x is one function, and the y is a separate function, right? That's two things multiplied together. Two functions multiplied, well, they may have functions, relations multiplied together. You've got to do a product rule on this. So, what's the product rule say? Derivative of the first. So, what's the derivative of negative 6x? Negative 6 with the y left alone. And then it's plus, I'm not going to write the plus yet because I know I'm going to get a negative in there. Plus the first one left alone. So that'd be negative 6x. And then what's the derivative of y? Y prime. Right? So we got to do a product rule. Got to do a product rule when you got that x times y thing. Pretty good. A hint, you're probably going to see that on the gateway test. If we do a couple of xy, next year xy kind of problem, probably going to be at least one that it gets something like that in.
Should you put parentheses around your 6y?
Here?
Yeah.
Don't need it. That's why I made sure to keep that negative with the 6 and everything.
So if you put like 10x minus, then you put a parenthesis there. Would that be wrong?
A parenthesis there, where would you be closing the parenthesis?
After the 6x multiply.
Well, then you better not have a minus here then. What I'm saying is if you do the minus and then you do your product rule just on these two, then it would be derivative of 6x would be 6, y left alone, plus, and then 6x left alone, and then y prime, and then you're going to have to distribute that negative. If you have a negative outside the parentheses and a negative here, then that becomes a plus, and that's bad. So that's why I'm saying if you just treat the negative and the 6 together, you can avoid having to put parentheses. You see what I mean? And avoid distributing. So that's why I would do it this way. Okay, plus, what's the derivative of 5y squared? Careful now. 10y, y prime. Do the normal derivative, which would be 10y, y prime. What would be the derivative of 6y to the 4th? Just tell me that real quick. 24, y to the 3rd, y prime. Right? You do the normal derivative, 24y to the 3rd, tack on a y prime. Okay, back to this. Equals 0, right? Because the derivative of 16 is 0. Now, we need to get the y prime by itself. So this is the first time this happens to us. We have two terms that have y prime in. So what do? Well, we're going to leave those on this side and we're going to move the other stuff over. So I'm going to leave negative 6x y prime here plus 10y y prime here. And on the other side, I'm going to have my 6y over there and my minus 10x. I'm going to move those over. What do you suppose I would now do on the left side? Factor out a y prime. So I want to gather my y prime terms on one side. Then I'm going to factor out a y prime. And then I can divide by that quantity. And so I get 6y minus 10x. All over negative 6x plus 10y, and that. Now, actually, I could simplify this, couldn't I? I could take out a 2 on the top and a 2 on the bottom and cancel them. And so it would really be 3y minus 5x. I think we should do that. And then it'd be negative 3x plus 5y on the bottom. That's what I think we should have. We could take out a 2 from the top and the bottom and we could cancel it. And there's your y prime right there. Okay? So this is called implicit differentiation. You're probably going to have 2 or at the most 3 of those of the 10. Probably not 3, no, probably 2 at the most. So you can actually get 8 out of 10 without even getting these right. But these aren't that bad. They're not, and we can make them messier, but we're not going to make them a whole lot messier. Okay? So on your homework sheet, it says it's got some problems for 3.3. It doesn't have a lot of them. Or is it 3.3? No, I wrote that wrong. It's 3.3, not 3.4. Yeah. Now, what I'd like for you to do, and again, how much you practice is really going to be up to you, but you trust me. You may, you do a few and you're like, I got the hang of this. And then you get to the gateway test and you get 4 because you make a lot of little mistakes. Because every time you practice these, you get better and better at recognizing, oh yeah, I got to do this here. Oh yeah, this is one of those where this happens. And, da-da-da. Trust me. Practice, practice. People that are successful on these typically have pages and pages of practice problems. So notice I said 3.3 homework and then plus 10 either on the website or from page 195 or whatever. Start doing that.
Okay, if we like the last one on simplified, if we get it wrong, we didn't take out the 2.
If you didn't take out the 2 on the gateway test, you would get it wrong. Especially on the first gateway test. Because on the first gateway test, if you get 8 out of 10, in the grade book, you get 30 out of 30, right? And I feel like you got to earn that, 30 out of 30, right? You already get a miss 2, right? Still get a 30 out of 30. Now, if you take subsequent ones, and you got 7, let's say, and and one of those was where you maybe just didn't simplify something kind of easy, then I've been known to give you that one so you pass it, right? But the first one, the one we do on Tuesday, your 8 that you get right got to really be right. So I'll be fairly picky on that.
On a regular gateway test, what's going to be the difference? I'm just
What do you mean? Like you got to take the second one, or what do you mean? Or,
like assuming one of them.
well, there's one gateway test right now for derivatives.
Is there one for a different subject?
Anti-derivatives later in the course.
Is it the same test?
No, each test is different. 10 different questions, yeah. 10 different questions each time.